November 7th, 1944. The forests of Lorraine, France. Oberleutnant Friedrich von Schell stood beside the smoking wreckage of his Panther AUSFG, watching his crew drag the charred body of his gunner from the turret hatch. The man had been 22 years old, a veteran of Kursk who had survived 2 years on the Eastern Front only to die here, in what should have been a routine engagement against American armor. Von Schell's hands were shaking, not from fear, but from something far more disturbing. Confusion. His Panther had been hit from the front at approximately 900 meters. The round had punched straight through the glacis plate, an 80mm slab of face-hardened steel angled at 55 degrees, giving it an effective thickness of over 140 millimeters. No known American weapon should have been able to do that. Not at that range. Not from that angle. As his surviving crew gathered around him in the cold autumn rain, Von Schell's mind kept returning to a single thought that violated everything he had been taught about armored warfare. What kind of shell could possibly do that? If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand what happened in that forest clearing, you need to understand the strategic situation American armor faced by the fall of 1944. The German Panther tank, first deployed at Kursk in July 1943, represented a quantum leap in tank design. Its combination of sloped armor, a powerful long-barreled 75mm KWK-42 gun, and relatively good mobility made it the most formidable medium tank in the world. American tank crews had learned to fear it. The M4 Sherman, America's primary battle tank, was designed in 1941 when the threats were Panzer IIIs and IVs. By 1944, it was hopelessly outmatched. The standard 75mm M3 gun could only penetrate about 60 millimeters of armor at 1,000 yards. Against a Panther's frontal armor, this was completely inadequate. Crews had to maneuver for flank shots, exposing themselves to devastating return fire from German guns that could kill them at ranges exceeding 2,000 yards. The mathematics was brutal. In Normandy during June and July 1944, after-action reports documented loss ratios approaching 5-to-1. For every Panther destroyed, the Americans lost 5 Shermans. General Dwight Eisenhower was receiving increasingly desperate reports from frontline commanders. The armor imbalance wasn't just a tactical problem, it was destroying morale. Tank crews were refusing to advance against known Panther positions. Some units were experiencing what would later be called combat exhaustion, at rates not seen since the worst days of World War I trench warfare. The U.S. Army's solution was the 76mm gun, a longer, more powerful weapon mounted on upgraded M4A1, M4A2, and M4A3 Shermans. The M1A1 76mm gun, firing standard M62 armor-piercing capped ballistic cap rounds, achieved a muzzle velocity of 792 meters per second. This gave it penetration of approximately 88 millimeters at 1,000 yards against vertical armor. Better than the 75mm gun, certainly, but still insufficient against a Panther's sloped frontal armor. American ordnance officers understood the problem. They needed either a much larger gun, which would require a completely new tank design, or they needed better ammunition. The gun solution would take years. The ammunition solution, if it could be made to work, could be fielded immediately to existing tanks already in Europe. The answer lay in a material that was becoming increasingly precious as the war consumed global resources. Tungsten. Tungsten carbide is one of the hardest substances known to materials science. When properly alloyed and formed into a penetrator core, it approaches the hardness of industrial diamond. Its density is 19.3 grams per cubic centimeter, nearly 2.5 times denser than steel. Most importantly, for armor-piercing applications, it maintains its structural integrity at extreme velocities and upon impact, where softer materials would shatter or deform. American metallurgists at the Watertown Arsenal in Massachusetts had been experimenting with tungsten carbide armor-piercing ammunition since early 1943. The concept was theoretically straightforward, but fiendishly difficult to implement in practice. You create a sub-caliber penetrator core of tungsten carbide, substantially smaller in diameter than the gun barrel. You encase this core in a lightweight jacket of aluminum alloy that fills the bore. When fired, the entire assembly travels down the barrel, but the lightweight jacket and dense core combination produces dramatically higher velocity than a conventional solid steel projectile of the same caliber. The result was designated the M93 hypervelocity armor-piercing round for the 76mm gun. The engineering was elegant. A tungsten carbide core, approximately 57mm in diameter and weighing roughly 2 kilograms, was wrapped in an aluminum alloy jacket machined to exactly 76mm to fit the gun bore. The overall projectile weight was significantly less than a solid steel round, which, when combined with a full propellant charge, produced a muzzle velocity of 1,036 meters per second. This represented a velocity increase of over 30% compared to standard M62 ammunition. The kinetic energy of a projectile increases with the square of velocity, meaning the M93 carried nearly 70% more energy than conventional rounds. In armor penetration terms, this was transformational. Aberdeen proving. Ground testing in Maryland during the summer of 1944 demonstrated penetration of 160 millimeters of rolled homogeneous armor at 1,000 yards. Against sloped armor equivalent to a Panther's glacis plate, the M93 could achieve penetration at combat ranges where German crews believed they were completely safe. For the first time since the Panther's introduction, American Shermans equipped with 76mm guns could engage German heavy armor frontally with a reasonable probability of penetration and kill. But there was a catastrophic problem that would limit the M93's impact throughout the war and beyond. Tungsten was desperately scarce. The United States had some domestic tungsten production, primarily from mines in California, Nevada, and Colorado, but these sources were insufficient for wartime demand. The world's largest tungsten deposits were in China, specifically in Jiangxi and Hunan provinces, but by 1943, Japanese occupation had cut off most of these supplies. Portugal had significant tungsten mines, but accessing Portuguese tungsten required complex diplomatic negotiations and shipping routes vulnerable to U-boat attack. More critically, tungsten wasn't just needed for ammunition. It was absolutely essential for industrial cutting tools. High-speed steel tool bits used in lathes, milling machines, and other manufacturing equipment required tungsten carbide to maintain their cutting edge when machining hardened steel. Every tank, every aircraft, every artillery piece produced by American industry required machine tools with tungsten carbide cutting surfaces. The War Production Board faced an impossible allocation decision: tungsten for HVAP ammunition or tungsten for the machine tools needed to produce tanks, aircraft, and artillery. The decision was made to prioritize industrial tooling. American war production depended on maintaining manufacturing capacity. Tank production, aircraft production, shipbuilding all required functional machine tools operating at peak efficiency. As a result, M93 HVAP production remained severely constrained. By late 1944, estimates suggest only about 3 to 5% of 76mm armor-piercing ammunition shipped to Europe was HVAP. Most Sherman tank crews received between 3 and 8 HVAP rounds per tank. Some units received none at all. Standing orders from higher command were explicit and inflexible. HVAP ammunition was to be used only against heavy German armor, Panthers and Tigers, nothing else. This scarcity had an unintended strategic consequence. The M93 HVAP remained largely unknown to German intelligence through most of 1944. Captured American tanks and ammunition stockpiles yielded primarily standard M62 rounds. German technical intelligence assessments continued to rate the 76mm gun as inferior to Panther frontal armor. This confidence would prove catastrophic. On September 18, 1944, German forces launched Operation Lüttich, later known to Americans as the Arracourt counteroffensive. The German 5th Panzer Army, reinforced with the newly arrived 111th and 113th Panzer Brigades, attacked American positions near Arracourt in eastern France. The objective was ambitious: cut off General George Patton's Third Army, recapture the Lorraine region, and stabilize the Western Front Before winter, the German attack force included over 200 Panther and Panzer IV tanks. It was one of the largest armored counteroffensives Germany would mount in the West during 1944. German commanders were confident. Intelligence indicated American armor remained vulnerable to Panther guns. The plan relied on German qualitative superiority in armor to overcome American numerical advantages. Opposing this force was the U.S. 4th Armored Division, including Lieutenant Colonel Creighton Abrams' 37th Tank Battalion. Abrams, who would later become Chief of Staff of the U.S. Army, was a hard-driving, tactically brilliant commander who understood armor warfare at an instinctive level. His battalion was equipped with M4A3 Sherman tanks mounting 76mm guns. Critically, they had received a small allocation of M93 HVAP ammunition, approximately 5 rounds per tank. Abrams issued clear, unambiguous orders to his tank commanders: save the HVAP for Panthers, make every shot count, do not waste this ammunition on soft targets or lighter German armor. When you see a Panther, load HVAP, take your time, and kill it. The German offensive began in heavy fog on the morning of September 19th. Visibility was limited to a few hundred meters in places. For German Panzer commanders, veterans of the brutal fighting on the Eastern Front, fog was an advantage. It negated American air superiority and forced close-range engagements where German armor and gunnery superiority would be decisive. As Panthers advanced through the morning mist near the village of Arracourt, their commanders expected to encounter American Shermans and destroy them systematically, as they had done so many times before. What they encountered instead was something that would shatter German armor doctrine and create a psychological crisis that rippled through Panzer forces for the remainder of the war. Sergeant Francis Baker was a gunner in Company C, 37th Tank Battalion. His Sherman was positioned in a hull-down firing position overlooking a road junction near Arracourt when 3 Panthers emerged from the fog at approximately 800 yards. Standard American doctrine for this situation was clear. You retreated or you maneuvered for flank shots. You did not engage Panthers frontally at medium range. That was suicide. But Baker's tank commander, Lieutenant James Leach, had HVAP loaded in the gun. He had been waiting for exactly this moment. His orders to Baker were calm and professional, despite the fact that they violated every tactical principle Baker had learned. Gunner, target Panther, front 800 yards. Load HVAP. Fire when ready. Baker laid the crosshairs on the lead Panther's glacis plate. The distinctive profile was unmistakable. 80mm frontal armor sloped at 55 degrees, impenetrable by any weapon Baker had used before. But he had been briefed on the HVAP ammunition. He had been told it would work. He had to trust that intelligence. He fired. The 76mm gun recoiled violently. Through the gun sight, Baker saw the tracer streak toward the Panther. The tungsten carbide core, traveling at over 1,000 meters per second, struck the glacis plate with a kinetic energy equivalent to a small bomb. The physics were unforgiving. The penetrator punched through the face-hardened steel, creating a shower of incandescent spall inside the crew compartment. The Panther's ammunition detonated instantly. The turret lifted off the hull in a catastrophic explosion. The German crew, those who survived the initial penetration, bailed out in shock. Baker traversed right to the second Panther. The German tank commander, seeing his lead vehicle explode, had stopped to assess. It was a fatal hesitation. Baker fired again. Another penetration, another catastrophic ammunition fire. The third Panther, its commander realizing the impossible was happening, attempted to reverse into the fog. Baker's third HVAP round caught it in the turret face at the base of the gun mantlet, a notoriously strong area. The round penetrated anyway. 3 shots, 3 dead Panthers, from the front, at ranges where German crews had believed themselves invulnerable. This pattern repeated across the Arracourt battlefield throughout September 19th and 20th. American tank crews, carefully rationing their precious HVAP ammunition, engaged Panthers frontally with devastating results. German after-action reports captured after the battle revealed the confusion and terror this created. One Panther commander reported, "Enemy tanks firing unknown ammunition type. Frontal armor defeats ineffective. Request immediate tactical guidance." Another report stated, "American 76mm gun penetrating glacis plate at ranges exceeding 700 meters. Previous intelligence assessments incorrect. Require immediate re-evaluation of American armor capabilities." Over 3 days of fighting, Abrams's 37th Tank Battalion and supporting units destroyed 86 German tanks. The vast majority were Panthers. American losses were 25 Shermans, giving a kill ratio of better than 3-1. For German Panzer forces that had grown accustomed to dominating American armor, Arracourt was a catastrophic reversal. But more than the tactical defeat, it was a psychological hammer blow. The myth of Panther invincibility, the one qualitative advantage that gave German tank crews confidence, despite overwhelming Allied numerical superiority, had been shattered. On November 7th, 1944, 3 weeks after Arracourt, Oberleutnant Friedrich von Schell was leading a 4-tank Panther platoon through the forests of Lorraine when his lead tank encountered what appeared to be an isolated American Sherman. At approximately 900 meters, von Schell, who had fought at Kursk and in Normandy, understood Panther tactics: engage at maximum range, use superior armor and gunnery to kill American tanks before they can maneuver for flank shots. His gunner fired. The round struck the Sherman, but failed to penetrate. A suspension hit, or a lucky angle. The Sherman, instead of retreating as doctrine dictated, returned fire. Von Schell saw the muzzle flash, and then his world exploded. The M93 HVAP round struck his Panther's glacis plate slightly right of center. The tungsten carbide core, still traveling at over 900 meters per second at that range, defeated the armor completely. Inside the crew compartment, the spalling effect was catastrophic. The driver and radio operator died instantly. The gunner was fatally wounded. Von Schell and his loader survived only because they were positioned higher in the turret. As his surviving crew abandoned the burning tank, von Schell looked back at the penetration hole. It was small, clean, nothing like the massive impact crater a conventional armor-piercing round would create. This had been something different, something new. German intelligence officers interrogated von Schell 3 days later at a field headquarters near Metz. They were desperately trying to understand what had happened at Arracourt and in subsequent engagements. Von Schell's account matched dozens of others. American Shermans were penetrating Panther frontal armor at medium range with an unknown ammunition type. On November 22, 1944, German forces finally recovered intact M93 HVAP rounds from a destroyed American ammunition truck near Saint-Avold. The rounds were shipped immediately to the Heereswaffenamt, the German Army Weapons Agency in Berlin, for technical analysis. What the German engineers found was both technically impressive and strategically devastating. The tungsten carbide core was immediately recognizable. It was nearly identical in concept to Germany's own Panzer 40 tungsten core ammunition, which had been developed in 1940 and 41. But Germany had been forced to abandon widespread use of tungsten ammunition by 1943 due to critical shortages. German tungsten supplies came primarily from Portugal and occupied France. By late 1943, Allied diplomatic pressure had reduced Portuguese tungsten exports to Germany to a trickle. French mines were producing at reduced capacity due to resistance sabotage and Allied bombing. Germany's remaining tungsten supplies were allocated to U-boat construction, where tungsten steel was essential for high-pressure hull components and to machine tool production. There was simply no tungsten available for ammunition production at scale. The fact that Americans were fielding tungsten core ammunition in combat, even in limited quantities, demonstrated an industrial and resource advantage that Germany could not possibly match. The technical report, prepared by Heereswaffenamt engineers, was classified as Geheim Kommandosache, top secret command matter. Its conclusions were carefully worded to avoid defeatism, but the implications were clear. The M93 HVAP represented a fundamental shift in the armor versus anti-armor equation on the Western Front. American tanks previously inferior to German armor in direct combat, could now engage Panthers frontally with significant probability of penetration at combat ranges. More troubling was the industrial calculation. If the Americans could produce and field tungsten ammunition, despite global tungsten scarcity, it indicated a level of resource access and industrial capacity that Germany, by late 1944, could not hope to match. The report noted that replicating the M93 would require tungsten allocations that would cripple U-boat production and machine tool manufacturing. It was an impossible choice, and the report recommended continued reliance on tactical superiority and prepared defensive positions to offset the new American ammunition capability. But for frontline Panzer crews, technical reports and strategic calculations were irrelevant. What mattered was the knowledge that their armor could be penetrated, that the one advantage they had relied upon, the one thing that had kept them alive through 2, 3, sometimes 4 years of war, was no longer certain. Reports from late 1944 describe a phenomenon German commanders began calling Panther Schreck, Panther fear, a hesitancy among tank crews to advance aggressively against American armor because any Sherman might be carrying the ammunition that could kill them frontally. This erosion of confidence had tangible tactical consequences. German armor became increasingly defensive, reluctant to conduct the aggressive maneuver warfare that had been the hallmark of Panzer doctrine. American forces noticed the change. After-action reports from December 1944 noted that German tank units were engaging at longer ranges and breaking contact more quickly when encountering resistance. This psychological advantage had shifted. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The M93 HVAP ammunition that destroyed von Schell's Panther and dozens of others at Arracourt and across the Western Front represented more than just advanced metallurgy. It represented the culmination of American industrial philosophy applied to the problem of armored warfare, where German engineering focused on creating superior individual weapons through technical sophistication. American engineering focused on creating adequate weapons that could be produced in overwhelming quantities and supported logistically. The M93 was never produced in sufficient quantities to completely change the character of the tank war in Europe. Tungsten scarcity ensured it remained a carefully rationed special weapon used only against the heaviest German armor. But at critical moments, in the hands of well-trained crews who understood its capabilities, it proved devastatingly effective. The ammunition didn't just penetrate armor, it penetrated the psychological confidence that had sustained German armored forces through years of increasingly desperate combat. For American tankers, the HVLP ammunition represented something profound, proof that their leadership was working to give them the tools they needed, evidence that American industrial might and scientific capability could overcome German technical advantages. Most importantly, it represented hope. They were no longer helpless against the Panthers. They could fight back. The winter of 1944 brought some of the most brutal fighting of the war. The Battle of the Bulge, Germany's last major offensive in the West, saw Panther and Tiger tanks deployed in numbers not seen since Normandy. But German tank commanders noticed something disturbing. American Sherman crews were no longer retreating when encountering heavy armor. They were engaging, and they were winning more often than German doctrine predicted. Interrogation reports of captured American tank crews revealed that HVAP ammunition, while still scarce, was being distributed more widely. By January 1945, some units were receiving up to 12 HVAP rounds per tank. It still wasn't enough to make HVAP standard ammunition, but it was enough to ensure that most engagements with German heavy armor would involve at least some HVAP-equipped tanks. The psychological impact on German panzer forces continued to deepen. Veteran crews who had survived years of combat on the Eastern Front, who had faced Soviet T-34s and IS-2s with confidence born from superior German engineering, were now hesitant to engage American armor. The certainty of their technical superiority had been shattered by a single type of ammunition they couldn't see until it was already killing them. German tank loss reports from the final months of the war tell a stark story. In engagements where German armor held positional advantage, where Panthers and Tigers should have dominated, loss ratios were approaching parity or worse. American after-action reports documented instances of German tanks withdrawing from favorable positions when engaged by 76mm Shermans, unable to determine whether they faced standard ammunition or the devastating HVAP rounds. But the true scale of the tungsten problem became clear only in the final accounting after Germany's surrender. When Allied intelligence teams examined captured German industrial facilities and ammunition stockpiles, they found virtually no tungsten core ammunition produced after late 1943. Germany's Panzer Granite 40 ammunition, technically similar to the American M93, existed only as small reserve stocks carefully hoarded for critical situations. The numbers revealed a resource war that Germany had been losing since 1942. American tungsten imports from China, despite Japanese occupation of coastal areas, continued through the war via difficult overland routes through Burma and India. Portuguese tungsten, despite German attempts to corner the market, continued flowing to Britain and the United States through aggressive Allied purchasing programs that outbid German offers. By 1945, American industry was processing approximately 3,000 tons of tungsten annually. Germany's tungsten availability had collapsed to less than 500 tons, almost all of which was allocated to machine tools and U-boat construction. The allocation for ammunition was effectively zero. This was the industrial mathematics that determined the war's outcome far more than any individual battle. The M93 HVAP story, however, did not end with Germany's surrender on May 8, 1945. The ammunition that had been developed to fight Panthers would find a new enemy in a new war within 5 years. On June 25, 1950, North Korean forces, equipped with Soviet T-34-85 medium tanks, crossed the 38th parallel and invaded South Korea. The initial American response force, Task Force Smith, was equipped with M24 Chaffee light tanks whose 37mm guns were completely inadequate against T-34 armor. The T-34-85 had 90mm of frontal armor sloped at 60 degrees, giving it an effective thickness approaching 150mm. Against the initial American forces in Korea, these Soviet-supplied tanks were devastatingly effective. Urgent requests went out for heavier American armor and better anti-armor weapons. M26 Pershing and M46 Patton tanks were rushed to Korea from occupation duty in Japan and from strategic reserves in the United States. But more importantly, vast stockpiles of M93 HVAP ammunition stored in depots since World War II were shipped to the peninsula. The tungsten core rounds that had killed Panthers at Arracourt would now face Soviet armor in the mountains and valleys of Korea. The 90mm gun on the M26 Pershing had been designed specifically to counter German heavy armor. When firing M93 HVAP ammunition adapted for the 90mm caliber, it could penetrate over 200mm of armor at 1,000 yards. Against T-34 armor, even at extended ranges, this was overwhelming. Combat reports from the tank battles of 1950 and 51 demonstrate the continued effectiveness of tungsten core ammunition. At the Battle of the Bowling Alley in August 1950, M26 Pershings, equipped with HVAP ammunition, engaged North Korean T-34s at ranges exceeding 1,500 yards. The American tanks achieved penetrations and kills at distances where the T-34s couldn't effectively return fire. The technological advantage had shifted decisively. The same ammunition that had evened the odds against Panthers now gave American armor complete dominance against Soviet designs. But tungsten scarcity remained a persistent problem, even in Korea. Despite 5 years of peace that should have allowed tungsten stockpile replenishment, HVAP ammunition was still carefully rationed, and tank crews received limited allocations and orders remained strict. Use HVAP against enemy armor only. Do not waste it on fortifications or soft targets. The strategic resource that had been scarce in 1944 was still scarce in 1950. The Korean War experience prompted serious re-evaluation of American anti-armor ammunition development. Tungsten, despite its effectiveness, could not be relied upon as the primary material for armor-piercing rounds. The supply was too uncertain, too vulnerable to disruption. American metallurgists and weapons designers began exploring alternatives. The answer they found was both controversial and brilliantly effective. Depleted uranium. Uranium depleted of its fissile isotopes through the enrichment process is even denser than tungsten, 19 grams per cubic centimeter, compared to tungsten's 19.3. More importantly, depleted uranium has a unique property called adiabatic shear. Upon high-velocity impact, depleted uranium penetrators self-sharpen rather than mushrooming like conventional materials. They essentially drill through armor while generating intense heat that can ignite ammunition and fuel inside the target. By the 1970s, depleted uranium had replaced tungsten as the primary material for American armor-piercing ammunition. The M735 round for the 105mm gun on the M60 Patton tank used a depleted uranium penetrator. When the M1 Abrams entered service in 1980, it was equipped with the M774 depleted uranium round. The modern descendant, the M829 series, represents the culmination of technologies pioneered with the M93 HVAP. The M829A4, currently in US service, fires a depleted uranium penetrator approximately 22 millimeters in diameter and nearly 800 millimeters long at velocities approaching 1,700 meters per second. The penetrator is encased in a sabot, a supporting shoe that falls away after the round leaves the barrel, exactly like the aluminum jacket on the M93 fell away in flight. The fundamental concept is identical. Dense, hard penetrator core, extremely high velocity. Kinetic energy defeats armor through pure physics. The M829A4 can penetrate over 900 millimeters of rolled homogeneous armor, equivalent at 2,000 meters. It can defeat every known tank armor system in the world. This capability traces directly back to the American metallurgists who solved the Panther problem in 1943 by developing tungsten carbide penetrators fired at hypervelocity. Technology has evolved, the materials changed, but the physics remained constant. What the M93 HVAP demonstrated, and what modern armor-piercing ammunition continues to prove, is that armor warfare is fundamentally a competition between kinetic energy and material strength. Whoever can deliver more energy to a smaller point wins. The Germans understood this intellectually, which is why they developed the long 75mm and 88mm guns with excellent muzzle velocity and penetration. But they couldn't sustain production of the ammunition that would have maximized these weapons' potential. America understood something more fundamental. Industrial capacity matters more than individual weapon superiority. A good weapon that can be produced in quantity and supplied reliably will defeat a superior weapon that exists only in limited numbers. The M93 HVAP was never available in the quantities American commanders wanted, but it was available in sufficient quantities to change battlefield outcomes at critical moments. That was enough. The story of the M93 HVAP is ultimately a story about resource access and industrial philosophy. Two nations face the same technical problem, how to penetrate increasingly thick armor. Both nations developed similar solutions involving tungsten carbide cores, but only one nation could actually produce and field the ammunition in quantities sufficient to matter tactically. The nation with access to tungsten supplies, with the industrial infrastructure to process and manufacture precision ammunition components, with the logistics to distribute specialized munitions to frontline units, won the resource war. Germany, by 1944, had lost access to most global tungsten supplies. Its industrial capacity was being systematically destroyed by Allied bombing. Its logistics were collapsing under the weight of multi-front warfare and partisan attacks. Even if German engineers designed a perfect tungsten core round, there was no tungsten to make it, no undamaged factory to produce it, and no reliable way to deliver it to the tanks that needed it. This was the mathematics of industrial warfare that the Nazi leadership never fully accepted. They believed that German technical superiority and ideological conviction would overcome material disadvantages. They designed magnificent tanks like the Panther and Tiger, fearsome weapons that could destroy any Allied tank in single combat. But they couldn't produce them in sufficient numbers, couldn't supply them with adequate ammunition and fuel, and couldn't maintain them in the field. Meanwhile, America produced adequate tanks by the tens of thousands, supplied them with increasingly effective ammunition, including the game-changing HVAP, and maintained logistical networks that kept operational readiness above 70% throughout the war. Adequate weapons in overwhelming quantity defeated superior weapons in limited quantity. The M93 HVAP was the perfect example of this philosophy. For the tank crews who fought at Arracourt in the Battle of the Bulge and in the final drive into Germany, the HVAP rounds were more than just effective ammunition. They were tangible proof that American industrial might could solve problems that had seemed insurmountable. They were evidence that somebody back home, in laboratories and factories thousands of miles from the front, was working to give frontline soldiers the tools they needed to survive and win. The psychological impact of having a weapon that worked, that could kill Panthers from the front, that could turn a Sherman into a genuine threat rather than a helpless victim, cannot be overstated. Morale among American tank crews improved markedly after HVAP became available. After-action reports noted increased willingness to engage German heavy armor, more aggressive tactical approaches, better overall combat effectiveness. For German tank crews, the psychological impact was exactly the opposite. The erosion of confidence in their armor's invulnerability created a defensive mindset that violated every principle of Panzer doctrine. German armor, which had dominated battlefields through aggressive maneuver and exploitation of technological superiority, became increasingly cautious and reactive. The fear that any engagement might be against an HVAP-equipped Sherman created a hesitancy that American commanders exploited ruthlessly. Friedrich von Schell, the Oberleutnant whose Panther was destroyed near Arracourt in November 1944, survived the war as a prisoner. In post-war interviews conducted by U.S. Army historical researchers, he described the moment his Panther was penetrated as the instant he knew Germany would lose, not because one tank was destroyed, but because it meant American industry had solved a problem German industry couldn't. Von Schell stated, "When I saw that penetration hole, I understood. They had found a way. We had been told American tanks were inferior. We had been told our armor was impenetrable. We had been told we had technological superiority that would win the war. All lies. The Americans had better ammunition than we did, and if they had better ammunition, they probably had better everything. The war was over. We just didn't know it yet." This understanding came too late for the thousands of German tank crews who died in the final year of the war. It came too late for the hundreds of thousands of soldiers on all sides who perished in a conflict that was decided more by industrial capacity than battlefield heroism. But von Schell's realization was accurate. By late 1944, Germany was fighting a war it had already lost on factory floors and in resource allocation meetings. The M93 HVAP ammunition, produced in frustratingly limited quantities due to tungsten scarcity, still represented an advantage Germany could not counter. It demonstrated that American metallurgy was world-class, that American industry could manufacture precision components to exacting tolerances, that American logistics could deliver specialized munitions to frontline units. Every aspect of this capability was something Germany could no longer match. When modern M1 Abrams tanks fire M29 depleted uranium penetrators in training or combat, they are using the direct descendants of the M93 HVAP that killed von Schell's Panther 80 years ago. Technology has evolved dramatically. Depleted uranium replaced tungsten. Sabots became more sophisticated. Velocities increased by over 60%. Penetration increased by more than 5 times. But the fundamental concept remains unchanged. A dense, hard penetrator fired at extreme velocity will defeat armor through kinetic energy. This principle, pioneered by American engineers trying to solve the Panther problem, defines modern armor warfare. The M93 wasn't just ammunition. It was the foundation of a technological approach that would dominate tank combat for the next 8 decades and counting. The scarcity of tungsten that limited M93 production throughout World War II taught American weapons developers a critical lesson. Dependence on strategically scarce materials creates vulnerabilities. This lesson directly influenced the decision to develop depleted uranium ammunition in the Cold War era. Depleted uranium, a byproduct of nuclear enrichment, was available in effectively unlimited quantities. It freed American anti-armor capability from dependence on tungsten supplies vulnerable to disruption. This strategic thinking, planning for material sustainability over decades, not just immediate wartime needs, gave the United States an enduring advantage in armored warfare technology. The Soviet Union and later Russia continued using tungsten core ammunition, remaining vulnerable to the same supply constraints that had limited German ammunition production in World War II. American forces using depleted uranium ammunition had no such constraints. The legacy of the M93 HVAP extends beyond just ammunition technology. It represents a philosophical approach to warfare that prioritizes industrial sustainability and resource access as strategic advantages equal to battlefield tactics. Wars are won not just by brave soldiers and brilliant generals, but by the nations that can produce, supply, and sustain their forces more effectively than their enemies. Germany learned this lesson too late. By the time German engineers analyzed captured M93 rounds in late 1944 and understood what they were facing, Germany lacked the industrial capacity and resource access to respond effectively. The tungsten that might have produced German equivalent ammunition was already committed to U-boats and machine tools. There were no reserves. There was no flexibility. The industrial war was lost. America, by contrast, maintained enough industrial flexibility to allocate scarce tungsten to HVAP production, even while sustaining machine tool manufacturing, even while producing tens of thousands of tanks and aircraft and ships. This flexibility, this ability to do multiple things adequately rather than one thing perfectly, defined American industrial strategy and ultimately American victory. The M93 high-velocity armor-piercing round was never the wonder weapon that some hoped it would be. Tungsten scarcity ensured it remained a specialty munition, carefully rationed, used only when absolutely necessary. But at critical moments, at Arracourt, in the Bulge, in Korea, in the hands of trained crews who understood its capabilities, it was devastating. It gave American armor a fighting chance against technically superior German tanks. It provided the margin that turned potential defeats into victories. For the veterans of those battles, the men who loaded HVAP rounds into their 76mm guns and engaged Panthers from the front, the ammunition represented something profound. Hope, proof that they weren't forgotten, evidence that American industry and American ingenuity were working to keep them alive. The golden bullets that let them fight back against an enemy that had seemed invincible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.